works. So suppose we have trajectories. So we consider a so-called multi-parameter process. It is that consists of all other processes as and we can move time independently for each. The interesting questions follows. What is the condition, for example, for the image of such process? So it is it exercises but today I will be more talking about another question, which is the second one. And what is the properties of this set? Well, in terms of Hausdorff measures. So it is well known that we can measure the trajectories of random processes in terms of Hausdorff measures, and sometimes we can claim that they have certain Hausdorff dimension. But for such process, multi-parameter process, it is not so well known. In fact, I do not know any general results of this type, so it is interesting, I think. So if also if anyone knows a very general result of this type, please give me the reference because I haven't found. There are some book by Hjdnf multi-parameter Markov process, but there they have only very special type of results and with very special type of processes. So not this uh, kind of general setup. So this is the question that I want to discuss today, and of course, the third idea is, of course, that we want this condition. If we have some conditions, we want them to be intuitively well understood. So, for example, we want them to be related to some geometrical properties of the process. So what it means is that I want to, for example, for the first question, I'm interested in possible alternative conditions for this, even though we might have some answers, but it is not always these answers are very convenient to work with. So this is why the third question. Of course, unfortunately, the main results that I wanted to show you today, I wasn't able to prove, hopefully yet. So there will be not so many results, but we can discuss the questions nevertheless. The first is basically the answer to the first question is by Fitzsimmons and Salisbury. They proved that well, they had some conditions on the process. I may not show all the conditions, but each process must be transient and symmetric in sense that they have a dual, which is the same. The process is dual to itself. And of course, I say with Lemag measure, but in their case, it was more general. So they have some general
Are they
conditions.
dependent? Elish, are they dependent or
Independent,
not?
independent. Oh, I will always consider independent. Here also independent. Yes. In their case, they were also independent. And they proved that if we look at this energy, yes, so then we can take infimum over all such measures, and if it's finite, then we have well, I hear that very general that probability. Oh, sorry, probability. Let me spell of x to visit b, but in fact, this probability here is kind of is related to some more complicated than usual type of probabilities. At the very least, you have to integrate the starting point over a big measure in order for this to be for this to consider such probability. I think it may be even enough, but I cannot say for sure. Um, yeah, so some kind of probability to visit the set will be positive if and only if this is finite. So in fact, we can also interpret this so in the following way. So this is the capacity of the set. So 1 over IB is some kind of capacity of the set. And in fact, they proved even more. They proved that this is uh, related to this probability that they found, but again, the probability is not real probability, but some interval of probabilities. So yeah, so what we know is that this question is related to such energy integral and whether it's finite or not. And here, look that we have as density a product of resolvents. So, for example, this density can be infinite even if x not equal to y. So, if I equal to yy, then this can be infinite, right? So, this can be infinite already. It is possible. So, and other coordinate of x may not be equal. So it is different from the classical potential theory. And therefore, I do not know even too many books about such kind of potentials. So this is a problem. Uh, So just to remind you the simple usual case of Brownian motion produces potentials of this type. Yes, so in general we can have r greater than 0. Sometimes even logarithmic potential is possible, and then we can look at capacity and define it in a similar way. And in terms, if we define capacity like this, then it is, I think, equivalent to defining capacities in as a standard potential theory via Sobolev space, for example. There are different definition of this capacity, but they, I think, are equivalent. I can give you exact reference, but I think it's well known. And what's important to me is that we have a Hausdorff measure
I'm
that is
sorry, in this formula with ER of mu and capacity of A, infimum is taken with respect to what?
to such measures
To such
that
measure.
they
Okay.
are probability
Mhm.
measures and
So R is
they
fixed, mu
yeah
is variable. Okay, thank you.
yes, mu is variable, of course. So here it is well-known capacity, as I said, and this is well-known Hausdorff measure in also in RD. And it is known, this theorem, I believe it's by Frossman. Anyway, I give a reference to book of Hoshnevi-san, which is book about multiple dimensional capacities. And in this book, you can find this theorem and its proof even. So it turns out that an exact capacity or exact dimension, capacity dimension of the set is related to the Hausdorff dimension of the set, which is such as, so that HS is will be 0 for higher and infinity for lower S. And the same can be done for capacities. And this is a theorem that relates in one direction. If capacity is greater than 0, then Hausdorff measure is greater than 0. And the other direction, if Hausdorff measure is greater than 0, then if we take a step back a little bit by in dimension, then capacity is greater than 0. And of course, there are more precise theorem relation of this capacity and this Hausdorff measure, but it is well known that they're related. So let me move on. The same can be done on Carnot groups. So what I'm doing here is I'm considering basically processes known as Brownian motion on Carnot group, which is a kind of Brownian motion on Lie group, because Carnot group is just a Lie group with a special structure. And because of this, we can have a corresponding process, which will be also which will be producing some kind of capacity, and R has to be, of course, selected specifically for this capacity to be related to the process. Yeah. But we can even forget all that, because in fact it is enough to assume that we have a metric space. So if we have a metric space, all these definitions are also valid. And we can define corresponding capacity again in the same way, and except here already we have distance instead of distance in Carnot group instead of distance in Euclidean space. And the same is here. B rho is both with respect to this distance rho. So this is just replacing the distance. We get the same definitions. And in fact, I found a paper where after simple proof the analog of Frossman theorem, the theorem of the previous slide, for this specific case. Except they did not use this capacity, and they use Bessel, so-called Ritz capacities or Bessel capacities, which is again capacities related to Sobolev spaces. But I think they also should be related to this capacity.
Alexei, I have a question related to your sentence that you said it is enough to consider the metric space. But in general, in metric space, the set of measures for which such integral has sense can be very pure, I think, yeah? In general metric space, you see? So I think that it is good to discuss Carnot group because we have a Lebesgue measure. Yeah.
What do you mean by that? What
I mean that
possibly happen?
okay, let instead RD we have a arbitrary some general metric space. What can you say about the existence of measures mu for which such integral is finite? Yeah.
Yeah, but definition still holds. Maybe the definition doesn't produce something meaningful in some cases. In this sense, it can be bad.
This is my point that maybe we have to consider still some structures where we have analog of Lebesgue measure.
Well, there are some. I did not say it's just because I like the generalization. There are some general results considering capacities and Hausdorff measures on general metric spaces, but of course there should be some assumptions, like maybe locally compact, some other things, of course, has to be assumed.
Okay.
Okay. So yeah, so we can have the same on the Carnot group, and the only addition is that I use a metric here on the Carnot group. And this is this, we have the similar relation, in fact. So now what I want to do is I want to define the capacity which is related to several processes in a sense that now I will consider several Carnot groups, and I will basically write what was obtained earlier by Fitzsimmons and Salisbury. So I will use the definition of capacity basically, and just extend it in the sense that I will use not just any power here. If I put exact value of qi minus 2, which is Qi is the homogeneous dimension of this space Ji. Yeah, so if I put it here, then this will be exactly related to the capacity in Fitzsimmons-Salisbury theorem. So this is this capacity, and now it is different. Now I do not know if it's related to any other type of capacities of the similar. I did not find it in literature. So again, if you can help me, the relation of such capacities with some differently defined capacities, like maybe some Sobolev, even some Sobolev spaces capacities. I do not know of such results. Yeah, but we still can define this capacity, and here I will compare these capacities with capacities of this type. So if well, it is very simple comparison, but it is useful because this capacities here, it is in fact capacities with respect to some distance. Well, this may not be distance, this is pseudo distance, but the definition from the previous slide still can be applied to this. So we have capacity from the previous slide is this capacity in fact. So if I, instead of product, I take minimum, we actually arrive to the case where we were on the previous slide, more or less. And in fact, I can compare these capacities from to this capacity in the following way, that there are some set of values such that if, for each value in this set, this capacity will be less, I'm sorry, this capacity will be greater than this capacity. And in terms of energy integral, of course, it's vice versa. It is very simple, it's trivial fact, but what it tells me is that at the very least, this capacity is less or equal infimum of such capacities over some set of P. So it is not, it is related in this way to the standard capacities. And here I cannot prove this, but I think that this is not equal to, so I will write it down. So this is, I think, not equal to infimum over O such P, but I cannot prove this at the moment. So this is a question mark, but intuitively it probably shouldn't happen. So it is not the same. This capacity is not the same as an infimum of such capacities, even though it might seem that it is possible, but I don't think so. Okay, so now the main definition. So what I want to do is I want to define some kind of Hausdorff measure related to these capacities from previous slides. And quite honestly, I'm not sure that my definition here is correct in the sense that it will be related in the same way as I want it to relate it to this capacity. But nevertheless, I can use this definition at least to prove some results. So what is the difference here from usual Hausdorff measure is that I have this condition instead of conditions that each radius is less than epsilon. I have the condition that the product of this n and some power less than epsilon. What does this mean? It means that we allow not only, for example, if n is equal to 2, other dimensions are 1, then what's written here is rectangles. And what I claim here is that the side of rectangles A and B, they have following relations that A in some power P1, B in power P2 less than epsilon. So, for example, if P1 equal P2 equal to 1, that means that the area is bounded by epsilon, and that is it. So we allow any rectangle with bounded area here to cover our set. It is, I do not know how good, how to work even with this definition entirely, but allowing this, of course, changes completely what we have. So it is some kind of different Hausdorff measure, and I think, if I'm not mistaken, this is will not be usual measure on Borel sets. At least there is a problem with proving that for sure. Of course, it is easy to check that this definition also gives us so-called Karateridori outer measure, right? So we have Karateridori outer measure, but then if we try to prove that Borel sets are measurable in the usual sense, yeah, but it might not be true, and the reason because we can have such long coverage, so we can have two sets which are side by side, two similar sets, yeah, and it is possible to cover them with the same set of balls simultaneously by extending this ball very, very far so that it covers both sets, yeah. And because of this, when we cover uh, uh, this set separately, this set separately, then there will be no additivity for this measure, yeah, on such two sets. It is clear that the covering can interact in this way. So there is a problem with additivity on Borel sets, and that's probably not measurable. But again, it has to be proved probably. Yeah, and again, if we modify this definition, instead of product we have maximum, then we return to the usual Hausdorff measures, and it is easy to see that this is Hausdorff measure that correspond to some row of this type. Again, may not be distance, but it is doesn't matter. We can still define it. It have similar properties as the distance. Triangle inequality with some constant is always true here. And just as with capacities, I can say that this Hausdorff measure that I defined is less or equal than Hausdorff measure of this type over some set of Q. And again, I suspect that this is not equal to infimum of this. Yeah, so by Q. But to prove it, I need to construct some special sets, so I did not do it today. But here I strongly believe that this is true. It has to be, because yeah, it would be strange if it just every set could be measured by measured by this measure also can be measured by some of these measures. It would be very strange. Okay. Just a second. Yeah, so now I want to prove some results. And unfortunately, this second result which is the question, I wasn't able to prove. So this is analog of Rossmann theorem. I want to prove is capacity. If capacity is positive, then corresponding Hausdorff measure is positive. This is, I think, approved. And then the reverse, if the capacity is positive, this S that I added, it was actually superficial because if we look back at the definition, if I replace here S equal to 1, we will basically have the same definition, because we can actually also look at the pi multiplied by S, right? And this will be the same as just as this definition. Yeah. Because this inequality just can be rewritten with different epsilon, and it will be the same. So S is not really needed, but it's useful, for example, in this case when I say that if S greater than 1, yeah, then maybe I can have that capacity is positive. But I wasn't able to prove this direction. Why I wasn't able to prove? Because in this direction, if we have positive Hausdorff measure, then the classical proof Frossman theorem requires us to build some kind of measure, and the construction is that we take our space, we divide our space into cells. It is even possible to do something like that on Carnot group, but then we have to define our measure on each cell. And the problem with this, because since I allowed for any rectangles to be in here, so my cell is not enough to define to define the measure, because I need to control not only measure of each cell but also measure of some kind of rectangles. Yeah, and this is a problem. And does not fit in the standard construction. So yeah, I wasn't able to modify it and obtain something, unfortunately. So it is a question. I do not know if it's even true, if this result is even true at the moment. Yeah, but this theorem we can prove. The proof is, yeah, and the proof is follows just usual proof of Frossman theorems, for example, can be found in Hjdnf or many other books, I'm sure. So if we have probability measure, and if we have corresponding energies finite, then we can just estimate the measure of such product of balls. This is just trivial. And then this is some kind of, this is Chebyshev inequality, basically. Yeah, using that supremum, but by this inequality, supremum is less or equal than this integral. Yeah, then we use Chebyshev inequality. We obtain this, and because of this, we can find such set that its measure is greater than or equal to 1/2. But on this set, we have this, and then of course, for any covering F with sets, yes, here we actually can do the following trick. We can change covering so that the centers will be in the set F, even with our rectangles. It's just we can do it by coordinate by coordinate, so it's not a problem. Maybe we have to double the radius or something, but I think it works. So we can assume that the centers are in F, and because of this, we have the result. So this is the proof of in this direction, and now let me continue. So now I want to prove the following result. Yeah, so suppose we have Brownian motions of Carnot group, and we have homogeneous dimensions Q1, Qn that of these groups, and we assume that they are greater than 2, which means that the process will be transient, for example. And then I want to estimate the Hausdorff measure in this new definition of the trajectories of the image of the process of all the trajectories intersecting with some bounded set. And the result is as follows. Well, I need a technical condition. Technical condition is at the starting point of the process, the x, which is here, is so that each coordinate, each xi is separated from this set. So, for example, if we have again n equal to 2, and just for simplicity, I will just do this in 2 dimensions. So if we have some set, yeah, so we look at the projections, and then our starting point cannot be in these projections. Its projections cannot be in this projection. So this is forbidden. So we can only be outside here somewhere, and cannot be here. It's not allowed. It is kind of restrictive, unfortunately, but it is needed here for the estimate. Yeah, so and the corresponding powers Q should be as follows. It's P, which is used here, minus Q plus 2. So they are smaller than P, each P by Q minus 2. And of course, we have to assume that P, each Pi was greater than Qi minus 2, otherwise this doesn't make sense. Okay. The proof goes like this. So I want to estimate I want to estimate how I cover the set with such sets. Yeah, our set, our set, our image of trajectories. Yeah, inside the set V with such set. So instead of considering all of the such coverings, I will consider coverings such that they are, we have some fixed number of sets that cover set V. So we have set V, and we have sets that cover set of this type that cover V. And then for each such set, we see if the process are actually, the image of the process are actually inside. And depending on this, we either include this in our covering or not. So, in fact, what is written here is what will be the value of Hausdorff measure or approximation of Hausdorff measure with such covering, right? And we can take expectation from this. And when we take expectation, it turns out that it can be estimated using this. So this is the probability of this each process to hit a ball. And this is well known for Brownian, well, it is possible to do for Brownian motion kernel group. And the estimate for each such probability is that it is less than or equal than Rij in power Q E minus 2. And this is why we have additional Qi minus 2 here. This is where it appears. And as a result, we see that the value of this Hausdorff measure is estimated by the value of P Hausdorff measure with power P. And this is basically the whole proof. So unfortunately, here I want supposed to be another theorem. So I will try to explain what I wanted to do, but yeah, I could not prove it, unfortunately. So what I also wanted to do is I wanted to have a reverse to this theorem. So I wanted to prove that such Hausdorff measure is also positive, yeah, for some Q under some conditions. And conditions, it is convenient to use, instead of Hausdorff measure for V, use capacity in the other direction. So we assume that capacity of V is finite, right? And then, sorry, not finite, it's positive, yeah. And then means that energy, corresponding energy integral is finite. This is what I meant. So if capacity is positive, then HMS PV intersect image X. I want to prove that this is also positive. So, and question mark because I do not know. And S has to be, okay, here it must be Q, not P. And actually Q is exactly the same as here. So this is what has to be here. So this is why I thought it would be good, because we have kind of two sides estimate for this. Yes. So we kind of have some kind of dimension even for this. If I were able to prove this, of course. And S has to be greater than 1. Yeah. This is because we have to step away a little bit in this direction always for some reason. When I do not know why, okay, but I needed this in any case. So and the typical proof would be like this. So I should construct. I have a measure mu that corresponds to this opacity. So I have a measure mu that make energy integral finite. So we take this measure mu and we construct some additive functional that related to this measure mu, and it is possible because we have because of work of Dinkin, he proved that additive functionals related to the set of to this family of independent Markov processes can be constructed. This belief in, I do not remember the name, but it was a 1981 work by Dinkin. And the condition is exactly that corresponding energy integral is finite. So it is exactly what I need. So I can construct corresponding additive functional, and then using this additive functional, I can make some estimates. But yeah, but it did not work out again because unfortunately I allowed the balls to be also rectangles, and it can be any rectangle. And because of this, the standard argument that is used, for example, by Legal in a similar situation, it doesn't work because I also need to take supremum over all possible rectangles, and it doesn't work. And this is unfortunately all that I can say today. Maybe if there are some questions, I can discuss it a little bit more. But for today, this is all.
Okay, thank you very much. If somebody have questions or comments, please. Okay, Alexei, I have the following question. I remember pioneering works of Taylor, where he discussed the Hausdorff dimension of the set of self-intersections of one Brownian motion or intersections of two independent Brownian motions. And as far as I remember, there is a more precise function than just powers. It contains, he defined Hausdorff measure, Hausdorff dimension related, Hausdorff measure, excuse me, related to the function like alpha multiply on logarithm alpha or something.
Yeah, so yes, actually even Legal also used such function, but the reason of this logarithm to appear is usually because we use usual distance. Maybe not. No. It is a difference. I'm sorry, I'm mixing it up. Yeah. So the reason for this logarithm to appear because usually because we need more. They want to be more precise. Yeah, this is one.
Yes, surely. So this is my idea. Maybe the idea that we relate this probability of visiting of some set by Brownian motion to this capacity related on the potential is only first step. I think that if we calculate Hausdorff measure more precisely of self-intersection, maybe more precisely we can define the Hausdorff measure of the sets. Then somewhere we will have sufficient and necessary conditions. Yeah, as you want actually.
So the more precise part relates to only one process, right?
at least it was in work of Taylor, but
Yeah, I will look. I actually think I know this works of Taylor. At least he had a lot of work in this direction for sure. So I will look again. But the problem here, because if you, I did not say that, but last time when I give you a talk, I basically did the same thing. But I looked at it and I think I decided that it doesn't work what I did last time. Why? Because I could not have a precise estimate like here. So I could not say that it is more or less the same estimate from above and below. So I decided to introduce this definition exactly for this reason, because we cannot have a precise estimate above and below with usual Hausdorff measures. So I thought. And I didn't see anywhere analogous estimates for this situation. So if you say Taylor has it, I will look, but I do
let
not
me
know.
ask you the following. I think that in Taylor work it is related to ideas based on the Wiener test, firstly, for Euclidean space, and secondly, even for one-dimensional case, we have a Kolmogorov functions, yes, which are like measure around for absolute value of the Wiener process. And then we need something like law of iterated logarithm, at least for beginning. Do we have something similar for Brownian motion on Carnot group? I think it must depend on the dimension, yeah?
Yes, it is possible to have some kind of, I think, but I do not understand the relation to the Hausdorff dimension of this product. Maybe
Because you see, when we have at least we can imagine when we have one self-intersection, at least in the usual Brownian case, we immediately have a lot of around, yeah.
yes,
And
yes.
this possibility arises exactly due to that we have a law of iterated logarithm. We can go up, go down, and when we have some independence, we have intersections for free. So here maybe the same arguments can be used, and I think I'm not sure right now, but I think that in those pioneering work, Taylor says that it is related to iterated logarithm. Yeah.
So again, the idea is that we fix one process and look at the other process how
Yes.
it fits.
Yeah.
I understand. So I used to I had an argument like this in the past, but the problem here is that I consider n processes. So if we have at least 3 processes, then it becomes complicated. So we have to consider hitting one process, not just another process, but already their intersection. So it kind of we have to iterate this procedure. It becomes more complicated. Maybe it's possible. I do not know.
Okay. Thank you.
Yeah, it
Thank
might be
you.
interesting to look at this way. Too. Yeah, thank you.
Maybe some other questions or comments, please. Okay, if there are no any other questions, thank you again for interesting talk about these geometric problems. And Georgi, do you know who will be next speaker?
Next speaker will be King Song Wang about
Oh, by the way, we planned
asymptotics or
with King
intersection
Song.
local times.
With King Song, Alexei, it will be interesting. It is related to your talk. We planned with King Song some review of papers, Koenig, Chen, on some small, large, moderate deviations for intersection local time. So it is closely related.
Okay, interesting.
Okay, then see you next week. Bye.
Okay, see you. Bye.
Bye. Thank you.